Now let's look a little closer at the penicillins, because these are a great example of how things change over time. You take a class of drugs, penicillin, okay? Penicillin, due to our going through and tweaking, are going through identifying new microbes that are public, that are producing this, and utilizing what we find, what we've characterized from new forms of penicillin to remaster the synthetic penicillin. You see, you look at the penicillins here in table 10.6. They all are based on that 2 rings. They call these 2 rings the 5-sided, the 6-sided, 2, 4, it's 5, 2, 4, 5. Whew, not enough caffeine yet. 5-sided ring, and then the 4-sided ring they call the beta-lactam ring. And then off the beta-lactam ring, you're going to find R group. R group here just means other things will be attached. These other things that are attached at the R group are going to give it some sort of ability, or it's going to give it some form of slightly different characteristic, make it more water soluble, going to make it narrower or broader spectrum based on what's been added. Look at the artist has shown here, penicillin G, methicillin, as losicillin, mesalazocillin, and ticarcillin. They all have the beta-lactam ring and the 5-sided ring with it. But it's what's attached to the beta-lactam ring is going to be slightly different, which means they are narrower or broader in spectrum. And it's also going to affect, what's there, that R group, whatever is added to the beta-lactam ring, is also going to slightly affect its activity. Penicillins all affect cell wall production. To what degree, to what species, to what gram-positive, gram-negative they can affect. It's going to be what's then been added. Here's the problem, though. When we talk drug resistance, penicillins is one of the most drug-resistant drugs out there. The reason being that beta-lactam ring. As the penicillin was the fungi were producing this compound, the original compound, microbes were also adapting, evolving defense mechanisms. One of the defense mechanisms they came up with was penicillinase. Penicillinase, anything that ends in A's means it's an enzyme. What prefaces A's is either its target or its activity. Penicillinase is an enzyme that cuts the beta-lactam ring. Change the shape, lose the function. So, the original bacteria that were resistant to penicillin evolved, adapted an enzyme that would cut the beta-lactam ring, basically giving us a compound that is the incorrect shape, thus has no function. Gene makes is the blueprint to make the enzyme. Enzyme does the cut. Bacteria is now saved from the weapon, penicillin. Over time, as we isolated and started using penicillin more and more often as the magic bullet, we were overusing it for bacterial infections, viral infections. Oh, you got a runny nose. Here, take this. Take penicillin. Take penicillin. We selected for microbes that had this penicillin A's ability. Turns out microbes, thanks to conjugation between species, bacteria of the same species, between different species, passed around the enzyme penicillinase. Not all the bacteria in a given area or a given infection will have the enzyme, the gene for the enzyme. So we pop the penicillin pills. All the microbes that don't have penicillinase die. Those that do have it are the only ones that remain. That's now become part of our normal flora. We cough, we sneeze, we kiss, we touch other people, we pass it to other people. Here, blah, blah, blah. You now have the bacteria on you, in you, that carry the gene for penicillinase. They're going to pass it around to other microbes. And before you know it, within a decade or so, the great magic bullet no longer worked. And that's what we see for a lot of the drugs.